Okay, so let's talk about section 1.6, allowable stress design. So when we're designing a system, when we're designing something or maybe analyzing something, we really need to be looking at the stress. We need to be looking at the stress because the stress is really what will cause something to fail. It's not the force. It's not like we need to make sure something doesn't exceed a certain force because, one object, a very thin beam, for instance, couldn't handle the same forces that a very large beam could. It's really the stress that we need to make sure our design can withstand. So that's allowable stress design. So let's kind of give it a little definition. To ensure safety in design, we must restrict the stress applied to one that is less than the stress the component can fully support. To one that is less than the stress the component can fully support. Right? So if we know the maximum stress, we need to make sure we don't exceed that maximum stress. So we can find the failure stress. So we can find the failure stress. So this would be the failure stress of the, and I'm going to say we're looking at a beam, but if we're looking at any object, the failure stress of the beam's material, whatever it is made of, and we get this from tests, from labs, that they can say, okay, this type of steel can withstand this maximum stress. So this is the stress that it will fail, or let's say the stress that it will start deforming. Will start deforming because we don't want any deformation, or at least any permanent deformation. All right, so if we know the maximum failure stress that this material can withstand, we need to make sure we don't go past that, right? And so we will set a factor of safety. So we will set a factor of safety, and so the factor of safety is going to be failure stress over allowable stress. Failure stress over allowable stress. So this is the allowable stress, and I'm going to say allowable stress that you, as a designer, as an engineer, will, allow to occur. All right. So for instance, maybe we'll have a factor of safety of 2. Right? Maybe we'll have a factor of safety of 2, and if we know the material can withstand 200 MPa, what are you going to allow? Right? What are you going to allow? This equation shows it, but at most of the time this is going to just be logical. This is going to make sense. If I use a factor of safety of 2, and if I know that it's probably going to fail, according to all these tests, the average stress that it will start deforming at is 200 MPa. Well, you're only going to allow it to get up to 100 MPa, right? You're going to say, don't exceed 100 MPa. That's going to be my maximum allowable stress that I'm going to let happen. Okay, so why are we using allowable stress design? Why are we using a factor of safety? Well, a lot of different reasons. All right, first, let's say load uncertainties. You may think that this beam needs to withstand this load, but what if it's a little bit more? What if it's not? What if it's not accurate, that load that you've calculated that it is going to withstand? You need to account for a factor of safety right there. Let's say fabrication, construction, and assembly errors. Maybe this pin wasn't exactly made as precise to the diameter that you think, or maybe it wasn't cut just right. Maybe there were some errors due to in the fabrication and construction process. Unknown forces may occur. Maybe you didn't account for some force that is happening in your system. The material may change over time. Material may change over time. You might have a variability of material properties. If you've got some sort of alloy or some steel, maybe it's not exactly the same as what your textbook thinks it should be, or what all the tests that say this material should hold up to 200 MPa, but maybe there's some variability in that. Calculation accuracy. Maybe we didn't do all those calculations correctly, and the one main thing is the risk involved. If this fails, what is going to happen? If you're just talking about a chair or something, someone might fall out of the chair. If you're talking about an elevator, that's or an airplane, right? Those are those are a little bit more risky. Maybe you use a larger factor of safety. Okay. All right, so for these allowable stress designs, there's kind of two main problems that we're going to come upon. You might know the sizing of all the pins and the cables and the beams. So you might know the sizing of, let's say, everything. And you're going to find the maximum load, or what's the maximum weight that this can withstand? What's the maximum force that this can withstand? Okay, or the kind of the opposite of that. You might know all the forces, and you might want to find a lot of times it's actually the minimum size that you need. What's the smallest pin that I can get? What's the smallest diameter of a cable that I can get so that it doesn't exceed the failure stress and the factor of safety, so that it doesn't exceed the allowable stress? Okay, so you need to make sure that the allowable stress for a normal force, you need to make sure that the normal stress doesn't exceed the allowable. So go ahead and say, okay, let's set my stress to the allowable stress. And normal stress we know is N over A. All right, so case number one, we know the area, the cross-sectional area of the cable. We know the stress we're trying to solve for. You know, what's the maximum N, or what's the maximum force. Or the other types of problem that we can do is this one. Maybe we know the force, we know the maximum stress. What's the minimum area? Right? You see how that two different types of problems that we can have. But make sure that go ahead and set your allowable stress to the allowable if you know the maximum stress, if you know the failure stress and the factor of safety, and then solve for what you need to solve for. So that's for the normal. You need to make sure it doesn't fail due to normal stress. So for cables, rods, you need to make sure that the normal force doesn't exceed the allowable. But then sometimes you need to be looking out for the shear force. You need to look out for the shear force and make sure your allowable shear stress isn't exceeded, the maximum isn't exceeded. So again, case number one, you know the area, you know the stress, you're trying to find the maximum V. Case number two, you know the stress and you know all the forces, you're trying to find the minimum area. All right, and so for pins are really the ones that fail under shear. Cables are the ones that fail under tension or normal stress. So not 100% always the time, but generally we got to check and make sure our pins don't fail under shear, and we got to check to make sure our cables don't fail under normal stress. Okay, so that's the main thing. Unless told otherwise, and I'll talk about a few different scenarios, but unless told otherwise, let's make sure our pins don't exceed their shear stress maximum. Let's make sure our cables don't exceed their normal stress maximum. Okay, some common applications. Sizing of a member. So this is a rod or a cable, and if we know that the force is 100 kips, we know the force over here is also 100 kips, and if we know it's going to fail at 36 KSI, and if we know we need to use a factor of safety of 2, then what size do we need? What is the diameter needed? What's really the minimum diameter needed? All right. Well, if it's going to fail at sigma failure of 36 KSI and a factor of safety of 2, here was my equation. Let's go up here. Factor of safety is sigma fail over sigma allowable. So 2 equals 36 over sigma allowable. Sigma allowable would be 18 KSI. And just make sure that makes sense. I have too many people who would kind of get this backwards and say, blah, 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 my allowable is 72. You know, that doesn't make sense that if it's going to fail at 36 that you're going to size it to 72. If you're going to, let's see here. Yeah. So, you know, if it's going to fail at 36, I'm only going to allow it to get up to 18. So let me allow it to get up to 18, and let me find the diameter. All right. So this is going to fail under normal stress. This is going to fail due to normal stress, or I'm going to make sure that it doesn't fail due to normal stress. All right, so sigma allowable is N over A. 18 KSI is an N of 100 kips. And KSI is just kips per square inch, right? Kips per square inch. So I've got to make sure my units on the left-hand side equal the units on the right-hand side. This is 100 kips per square inch. So this is a circular rod. The normal area, if it's going to fail, this circular cross-section is the failure area. So this would be pi by 4 diameter squared. So I can solve for the diameter. The diameter would be 2.66 inches. That would be the minimum diameter that I'm going to allow. I'll allow 3 inches, I'll allow 5 inches, I'll allow 10 inches, but the minimum diameter is 2.66 because that would cause a stress of 18, and I know it's going to fail at 36. So I'm only going to allow a diameter that would cause a stress of 18 if I know all the labs tests say it's going to fail if it gets up to 36. I'm only going to allow it to get up to 18, and that's the diameter that it would get up. So there's an example of sizing a normal force member, a cable or a rod, due to normal stress. Okay. All right, now, I said that most of the time pins fail due to shear. So let's say most of the time we need to make sure our pins don't fail under shear stress. We need to kind of test for shear failure. If we go back all the way back into our notes, let's see, to these, right? This is probably how our pin is going to fail. So we need to calculate the shear stress, make sure the shear stress doesn't exceed the maximum or the allowable. So we would calculate shear stress and make sure that shear stress doesn't exceed the maximum allowable shear stress. Okay, but if we're told to make sure it doesn't fail due to bearing stress, then this is what we're going to have to do. So we might need to calculate the area to resist bearing failure. Okay, so bearing stress is the normal stress, not the shear stress, but the normal stress produced by the compression of one surface against another. I like to think of it as kind of a crushing failure or a crushing stress. All right, so let's say, maybe this is 80 kilonewtons right here. Yes, it may fail right here due to shear, but it could actually get crushed right here due to this 80 kilonewton force right there. So this 80 kilonewton force is kind of really applied right here on the beam. So we need to make sure that 80 kilonewton force doesn't crush the pin. So, need to make sure that 80 or whatever force we have at the pin, force, doesn't exceed the maximum bearing stress. Okay, so we need to make sure that 80 kilonewton force doesn't exceed the maximum bearing stress. Well, that's a force, but we need to make sure it doesn't exceed a stress. So we need to consider the area this 80 kilonewton force is acting on. We need to consider the area this 80 kilonewton force is acting on. All right, so if we look at that, what area that's acting on, I'm going to attempt to draw this green section of the pin. All right, so here's the green section of the pin. All right, so that 80 kilonewton force is acting all the way around here, and it's really kind of acting like this. It's kind of small right here, it gets larger, gets larger, gets larger. It's acting, this is a terrible drawing, but anyway, it's acting all the way on this half of the circumference of the pin. It's acting on the outer edge of the pin, but it's not acting uniformly. Alright, this is what we can do. This is our trick. Instead of thinking about that 80 kilonewton force acting on the outside of that pin, I'm going to cut this pin in half. Cut pin in half. So now, see how I've cut this pin in half? I'm just going to say that this 80 kilonewton force is acting on this area of the pin. This 80 kilonewton force is acting on this area of the pin. And what is this area? So this is the area for calculating bearing stress. This would be this dimension right here is the diameter of the pin. Right, that dimension is the diameter of the pin. And this dimension right here is the thickness of the plate or this rod or you know, this beam. That would be the thickness right here of that plate. Okay, so the area for calculating bearing stress, that was a terrible drawing, probably a terrible explanation. But the area we need to use for calculating bearing stress is this rectangle right here that is diameter of the pin times the thickness of the plate. Diameter of pin times the thickness of the plate. Alright, so I'm going to leave it right there. You can review that. Check out Structure Free. That's the YouTube channel that I told you about. He does some great videos on just about every topic in this course. So after watching this video, look at some of his videos to help you prepare and understand these allowable stress design problems.